Hi, my name's Shivani, and my project is on the time dilation felt in the survival radius of a black hole. So, firstly, I focused on the idea that time is relative, and this is based on the theory of relativity by Einstein, which stated that time is malleable, meaning the greater an object's mass is, the greater gravitational force it has, and the greater time dilation is felt near that large mass object. So Einstein brought into light the theory of relativity, where mass, gravity, and time were all correlated in the way I just explained. This theory stated groundbreakingly that gravity had an effect on time. The closer you were to a larger mass object with a stronger gravitational force, the slower time went. So the purpose of my study on the effects that black holes have on time dilation was firstly to study time dilation felt near black holes, which are objects of extremely large mass. Secondly, I wanted to study and understand the possibilities of time travel utilizing time dilation near black holes. So, utilizing what we have as our resources today and what we know about the theory of general relativity, I wanted to figure out with our technology, could we possibly travel into the future and would that be possible? And also, I wanted to study how black holes have an extremely large mass and how that extremely large mass could lead to time dilation, how it affects time. So the research tools I used was Schwarzschild radius in relation to survival temperature. So the parameters of my research were pretty much trying to find a way to time travel in a distance that was safe, because as you get extremely close to a black hole, in turn it becomes extremely hot. Therefore, I needed to take this into account if I wanted to make it possible for a human being to actually go near a black hole and feel its effects without getting sucked in or without being burned to death. And that's why I also needed to take into account the temperature and the Schwarzschild radius, and which was the radius from the center of the black hole at which I needed to stay away from in order to not reach the temperature in which someone would die. So the black holes I studied were Cygnus X1, GRO J16540, and then the black hole in the center of our universe, which is Sagittarius A. So I just focused on the calculations for time dilation near Cygnus X1 in order to break down the method I used because it was quite extensive. Furthermore, it turns out that the time dilation near all the black holes were quite similar because all of them were quite similar in mass, and they also were all very you had to stay a certain radius away from them. So regardless of the small discrepancies in the mass, the radius that you had to stay away to survive made the time dilation very similar for all the black holes used. So here I just focused on Cygnus X1. So Cygnus has a mass of 21.2 million solar masses, meaning its mass is 21.2 million times the mass of the sun. It had a Schwarzschild radius of 44 kilometers. This was the length from the center of the black hole, Cygnus X1, to the survival or the radius of the actual black hole itself. So the Schwarzschild radius is the radius below which the gravitational attraction between the particles of a body must cause it to undergo irreversible gravitational collapse. So this is the radius in which a particle would not collapse when it went close enough. So this is kind of like the survival, but for particles. And then the survival radius for a human being, not a particle, would be 2.76 million kilometers away from the center of Cygnus X1 if the human being wanted to survive. And the spin parameter of the black hole itself, because black holes do spin slightly, was 0.95, which is a high spin parameter, meaning it's spinning very fast. Next, the survival radius. So in order to calculate the survival radius, I had to use the equations using the radius of Cygnus x1, as well as the survival radius for which the temperature was low enough for a human being to survive at. So using this equation, I was able to come up with the radius that our survival was 2.76 million kilometers. Then I wanted to find the survival temperature at this distance, and I was able to find that negative T naught, which is the temperature at the black hole, is equal to 0.1 Kelvin, and that I needed to use the equation for the temperature at black holes as found in a document on the temperatures near extremely large black holes such as Cygnus X1 and Sagittarius A. I was able to plug in the numbers I know of my radius, my Schwarzschild radius, and my survival radius in order to find the temperature at 2.676 million kilometers away, which would be approximately 1,644 Kelvin is equal to 1 keV. So therefore, I was able to figure out that the temperature would be about 0.001417, which equals about 440 kilometers per radius to the 0.75 power. So overall, this is the temperature at which a person could survive in a spaceship, of course, if they came near the black hole, using an equation found specifically for supermassive black holes. Next, using gravitational redshift, means that when light is moving away, it is redshifted, and when light is moving towards an object, it is blue shifted. So in this case, I wanted to calculate the gravitational redshift of the human would see near the black hole. So how would they view Earth from the black hole, or the point at which they were away from the black hole? So in order to find this, I used the gravitational redshift equation, and I found that the gravitational redshift is equal to 1 plus 8 times 10 to the negative 6th power. And then using this, I was able to find that the temperature when you go infinitely far away was 8 times 10 to the negative 6th. So overall, using gravitational redshift, using temperature, and using the survival and Schwarzschild radius, I was able to find the time shift using gravitational redshift comparatively from Earth to the distance from black hole. So the gravitational redshift was utilized in order to find the time difference between Earth and the point at which you were away from the black hole, or at a survival radius from Cygnus x1. So I found that 1 year of life would equal 8 times 10 to the negative 6 times to the negative 1, which means that in order to pass 1 full year of life in difference from Cygnus x1, you would have to say 125,786 years on Cygnus x1. This means that though the time difference is there, meaning Cygnus x1 is going slower than on Earth, the survival radius at which a human being could survive was so far away that the time dilation felt by the gravitational pull from the black hole was not significant enough to create enough time dilation for a human being to be able to survive enough time for 1 year of time to pass on Earth. Pretty much overall, this states that you would have to stay on Cygnus or near Cygnus x1 at the survival radius for about 100,000 years in order to feel 1 year of life off on Earth, which is well past any human being's ability to survive, and therefore it is improbable for a human being to feel time dilation or time travel into the future using this method, as the survival radius away from the black hole took away the significant time dilation felt. So in conclusion, time dilation felt near a black hole, especially supermassive black holes like Cygnus x1, is extremely significant. However, because I was at a Schwarzschild or a survival radius of over 1 million kilometers, it was a significant distance that made the time dilation not as significant because I was so far away from the black hole, I didn't feel as strong of the gravitational pull. Black holes make time slow down, but in the survival radius, time slowing is not significant, again, because of how far you are away from the black hole. So, a person would die before they felt 1 year pass on Earth, meaning that in order to have the time difference from Cygnus X1 to Earth be over a year for the person at Cygnus X1, they would have to stay for over 100,000 years at the survival radius from Cygnus X1 in order to feel the 1 year time dilation here on Earth, therefore making it improbable to use this method as a form of time travel. These are the sources I used: Reynolds, Mark T., and John M. Miller. I used this to find my equation for my survival temperature, as well as my redshift, gravitational redshift, for extremely large mass black holes such as Cygnus X1. And then I used Ronaska A, X-ray observations of the hot face in Sagittarius A, in order to find the temperature for my other black hole, Sagittarius A, which I did not use in this presentation. Thank you and have a nice day.